I want to introduce Dr. David LeBlanc. All yours.
Thank you very much. Okay, I'm from Canada. We know we're not going to do it alone, and I'd encourage you to try to get in that frame of mind a bit. It's not the US only, or France only, or Japan only, or, well, it could be China only. But beyond that, there's a lot of work to do. We should be helping each other. My field is on the actual core design, so I'll try to give you a little bit of basics and try to tell you where generally things are going in the world. Thorium is not fissile on its own. It doesn't fission on its own. We need a little bit of fissile material to start these up. Once started, though, we can run these on cheap and abundant thorium and keep the reactor going indefinitely on this. Great thing with thorium and the U-233, that chain, it can be done in any type of neutron spectrum, from the more common thermal to the less used fast spectrum. Processing of thorium, or processing in general, is extremely difficult for solid fuel reactors. That's why there's a little bit of interest worldwide, but really not that much. But since we're dealing with fluids here, it's much simpler for fluid fuels like our molten salts. It's easier processing, but it's still a challenge, and there's going to be a lot of R&D money needed to bring that forward. Without processing, thorium can be used with the aid of uranium. A little bit of low-enriched uranium can yield far superior what we call converter reactors, or the simpler burner reactors, than our current light water reactors, LWRs. Now, a little bit of basics about molten salt reactors. Molten salt reactors is the more broader term. Lifter is a bit narrower and a bit newer. But in general, our fuel, which is thorium and or uranium and or plutonium, it's dissolved in a carrier salt. FLiBe is one of the examples, enriched lithium and beryllium fluoride. This fluid fuel is also the coolant, and that carries heat energy out of the core to heat exchangers. It's a very high temperature operation, typically around 700 degrees, so that couples very well to almost any kind of power system you might imagine. A lot of us are going to be talking about Brayton systems, supercritical carbon dioxide, helium, etc., but it matches very well to general ultra supercritical steam as well, what the coal burners are using right now. So we can use off-the-shelf technology as well, even things like open air cycles. The textbook design is called the single fluid, graphite moderated molten salt breeder reactor. This is straight out of the Gen 4 program, Generation 4 program, to look at advanced reactors for the future. This is one of 6 of them. In this design, the core itself is just a large tank filled with graphite logs, basically, that the fuel salt flows in, and in the reactor it's critical, so heat's generated. Then that same fuel salt flows out to a heat exchanger, gives its heat to clean salt, and then that clean salt will either, in this diagram, to a Brayton cycle, or like I said, could be steam, could be almost anything. Near the bottom we have this freeze plug. So basically anything goes wrong, we lose power, etc., that freeze plug will melt, and the salts are drained to tanks that are specifically built to deal with that decay heat. There's a lot of design choices. One is breeder versus converter. Breeder means it makes your own fuel after you start it up. And if we just make just enough to keep going, that's nice because we don't have to worry about shipping out any fissile material, etc. We call that break-even breeding, and most of us feel that's the way we should be going. That requires the processing of the fission products to continuously, fairly slowly, but continuously remove them. So we might need some enrichment plants now to get them going, but once we're going on them, we don't need enrichment plants anymore. Converter reactors, on the other hand, we need some annual fissile makeup, which is typically going to be low-enriched uranium. But that skips fuel processing, or at least skips it for decades, and we do it once at the end of the sort of lifetime of the salt, etc. Much less R&D needed, much simpler designs. We're much more ready to go with things, and the core design is typically much simplified. There's also what we call the single fluid or two fluid, and even confusing, there's something called a 1.5 fluid. Single fluid, everything is one carrier salt, as is fairly obvious. The core design is typically a fair bit simpler this way. Processing, though, to remove those fission products is a lot harder. It's not as hard as solid fuels, but it's the hardest way with liquid fuels because thorium itself is very, very chemically similar to the rare earth fission products that are the most important ones to remove. Two fluid designs, on the other hand, they have a separate salt for the thorium that sort of catches neutrons, and a fuel salt for the uranium-233 that blanket salt produces. Fission product removal is a lot simpler because the fission products are produced in the fuel salt and there's no thorium there, so it's a lot easier. Core design was thought to be a lot more complex. What Oak Ridge looked at, Oak Ridge developed these in the 50s, 60s, and 70s. The design they looked at was very complicated. We think there's a lot easier ways to do this now. But pretty much any kind of two-fluid design, we have to verify these barrier materials. It could be even graphite itself, but a lot of different choices to separate those two salts. Shouldn't be very hard, but it's something we need to do, and anything nuclear can be quite expensive. Then we have either harder or softer spectrum between thermal and fast spectrums. Harder spectrum or fast, we can skip using graphite. Graphite's not really that hard to use with these reactors, but if we can get rid of it, it's probably a good idea too. Just one less thing to worry about. Easier to breed, we get sort of more neutrons per fission, etc. Although it typically takes a lot more fissile material to start up, and there's some exceptions, but that's a general rule of thumb. And avoiding what I call neutron leakage can be a problem. In a harder spectrum design, it can be, and especially in the single fluid, harder to avoid losing a lot of neutrons to leakage. We have this sort of neutron budget that we have to worry about. With a softer spectrum, control is a lot easier as well. Things happen a lot slower with thermal neutrons. Much smaller fissile material to start up, but we need to remove those fission products faster if we want to breed or break even. Now, my main design efforts have been in a two-fluid design, what's called a tube within tube. Hopefully solves what Oak Ridge often term their plumbing problem, which is the complexity they had to deal with. It's a very simple geometric sort of trick, in a sense, to get good size power cores out of this two-fluid design with a much simpler plumbing, so to speak. I sort of consider it high performance, biggest bang for your buck, but there's significant R&D needed in this design and in most designs. My other main focus for the last couple of years has been on what's called the denatured molten salt reactor, Th-MSR. This was developed in the late 70s at Oak Ridge National Labs. It's a really simple design. It's basically just a larger version of the test reactor that they built in the 60s, so a lot less R&D needed. And now it doesn't break even, so it needs a little bit of manual fuel, which is low enriched uranium, which is very, very much available. So it uses a mix of low enriched uranium and thorium. Most of the energy comes from thorium, but it's sort of helped along by that low enriched uranium. Now, since October 2010, though, to use a term Jim Kennedy was using about the Chinese sometimes, I've sort of gone dark. So I've been working on a lot of new areas, but instead of going public right away with a lot of them, I'm keeping things a bit secret, so sorry, no hints, but quite excited, looking forward to sharing these with you. Now, how do you judge a reactor in general? And that then guides us to what sort of design criteria we should choose. Of course, safety, cost, resource sustainability, and long-lived waste. I think these are really the most important, and pretty much every design we look at with molten salt reactors, these issues are very similar. What can be a little bit different between designs is proliferation resistance. We have a good story in all our different types of designs, and it's a bit of apples and oranges comparison. It's hard to make a really detailed comparison, but I think some can be labeled as extremely high proliferation resistance. Rapid deployment capability. If we want to build these by the hundreds or thousands to really make a difference, can we? And there can be some differences there. And then technological uncertainty, how much R&D we're going to need to move forward. Now, as I say, advantages of all molten salt reactors is the safety. We don't have large pressure vessels that could possibly fail. There's really no chemical driving forces here. We have no water, so no steam or explosions or hydrogen production. We have no zirconium water interactions, etc. The graphite can technically burn, but that's about all it can do. And it's very simple to avoid that. And of course, some of our designs don't even have graphite. There is almost no volatile fission products in the salt. All these accidents, Chernobyl, Fukushima, it's the volatile things that'll go off into the air and spread out. That's the real issue. It's almost impossible to imagine how radiation can be spread from a nuclear reactor beyond these things. They get into bizarre, the corium hitting water in a certain way, water getting inside the corium and then exploding. They really have to be imaginative beyond these volatile. But with the molten salts, those volatile elements, they come out naturally. They come out while we're running. We collect them, store them completely separate from the reactor. So if anything goes wrong, even a terrorist attack, a missile strike, etc., you might splash some salt around, but it basically lands and hardens, and very, very little will come out of it. We don't need any excess reactivity. There's no sort of shim rods or control rods that could be accidentally removed. We don't need any of that. They're very stable with instantly acting negative temperature reactivity coefficients. And again, we have that freeze valve to to lead the core, lead the heat to where we can deal with the decay heat best. Low capital costs. Molten salts in general, this is not quite as well known. They're just in general excellent coolants, much better than water, much better than liquid sodium, etc. So your pumps are smaller, the heat exchangers are smaller, and that makes things a lot easier to fabricate. This has a trickle-down effect on your building layout, construction schedules, factory fabrication, etc. Of course, we have a much higher thermal efficiency, 44%. We could probably push 50% with these on our various choices, and that's another wonderful thing, that we have so many choices. And of course, the fuel cycle costs are very, very low, and no need, since we have all this sort of passive safety, things happen by physics, not by engineering design. We don't have that defense in depth or these massive internal structures to deal with steam containment and vast water reserves to deal with that. Just looking at the size of the heat exchangers on the far left, we have the primary heat exchanger. We need 4 of those for a 1,000 megawatt plant and 16 of these tiny little steam generator tubes, versus in the middle 4 of those very large 70-foot tall steam generators that the PWR folks need to work with. And the sodium cooled fast reactor people, they love to show how tiny the reactor is itself, but they tend to neglect showing the absolutely massive water to liquid sodium steam generators and, well, their primary heat exchangers as well. So their volume is just an enormous factor compared to ours. Resource sustainability. Once we start these breeder reactor designs, if we're running them as breeders, all we need is just minor amounts of thorium a year. So about $30,000 worth of thorium gives you, well, it depends on your price per kilowatt, about $500 million worth of electricity. Converter designs are a lot simpler, and they do require some uranium, but very modest amounts. Typically, Oak Ridge's base design, and we can improve on that, was about 35 tons of uranium per gigawatt year, 1,000 megawatt plant running for a year, versus about 200 tons for light water reactors. And that gets a fuel cycle cost under 1/10 of a cent per kilowatt hour, so there's not too much room for improvement there anyway. And I would bring that up. Uranium is not really the enemy. Thorium isn't amazing on its own, but these reactors can help us use uranium a lot better as well. We're not going to run out of uranium in 80 years. We can run out of cheap uranium, and that can start to hurt the light water folks because they need so much of it. But when you talk, if you can find some competent geologists that know their field, they will tell you that there's no way that the uranium could ever be really more than $500 a kilogram, because then we just have so much low-grade ores that would be economical viable there. And even at $500 a kilogram in these designs that use it, that's still only a couple tenths of a cent per kilowatt hour. Now, mining is maybe not pretty in general, but 1.7 million tons of uranium ore that's dug up in, well, 2009 at a world average of 3% ore grade. You have to compare that. Mining's not pretty, but there's 2,500 million tons of copper ore, 1,700 million tons of iron ore, and 7 billion tons of coal. So the mining picture here is a pretty minor one. And if uranium is used with thorium in the Th-MSR designs, we could have 100% of the world's electricity, 2,500 gigawatts, without increasing the mining we're doing already. And even if we needed to go over to very low-grade ores where it might cost $500 a kilogram, but there's almost unlimited supplies then, that's still only a couple of hundred million tons of ore mined per year. Long-lived waste, that's another great story for molten salt reactors, Lifter in general. The fission products were very similar to almost any reactor design, but they're almost all relatively benign after a few hundred years. The real problem is what we call the transuranics, things above uranium, neptunium, specifically plutonium, and even above that. That's the real reason you have Yucca Mountains, which are, they're repositories. They're built so that 100 years later we can sort of come back and take that out, because you also don't want to bury plutonium for generations. All the molten salt reactor designs, regardless of they produce a lot less transuranics, and we can all just keep them in the salt, or every time we process, make sure we put them back in the salt. It's surprising to many, but I can show you the numbers if you don't believe me. Converters can do just as well as breeders in that. Converters will produce a little more plutonium a year, but you only have to process it every 10, 20, 30 years, so the picture can look just as well. That blue line is the actinide waste, that's the transuranics, and that's what is so nasty for so long, and this is logarithmic on both scales, so going out into millions of years. That's what takes so long. The dashed line is the fission products, and they drop like a rock for the first few hundred years, and then there's a few left that they're just low energy beta emitters, etc. Nothing too much to be concerned with. The blue line shows for a fast breeder, the sodium guys, and then this green line is for the molten salt breeder reactor, and that would be a very similar line for even the converter reactors. These arrows I have on the side, PWR use, Th-MSR, and then the MSBR on thorium, that shows sort of when we run these reactors, how much radiotoxicity we're actually destroying in the world or transmuting. And the Th-MSR design, we can do pretty much as well as the breeder, but we actually destroy a lot more natural radiotoxicity. So it's probably the only reactor design in the world that can make the claim that when you run these reactors 300 years later, when the fission products have died away, we've actually lowered the world's radiotoxicity. Okay, no other design. So we're doing the world a favor doing that. Now, proliferation resistance is mainly a political issue, okay? If a country wants it, they're going to build simple graphite pile reactors, etc. It's not really a technological issue. But that said, we still should do whatever we can to maximize proliferation resistance of designs. Now, I will mention, though, that the media often portrays thorium as somehow eliminating proliferation concerns altogether. This is not true, and that's important to understand. It can really help us, but it's still something we have to be vigilant about. Proliferation resistance of the pure cycle, what we maybe call the breeder cycle, the big benefit is from something called uranium-232. It's there a long time. It's got a 69-year half-life, and one of its daughter products makes a really high-energy gamma ray. Extremely easy to detect if anyone was trying to smuggle this around, and makes it really hard to work with. And no national program has ever been based on uranium-233. We can also instantly denature these by dumping in uranium-238, and that makes the uranium useless for any kind of weapons. Protactinium removal, I won't get into details here, but that can be eliminated in any design, even single fluids, believe it or not, for those that know a little bit here. But that should be avoided because that can lead to what you call clean 233 that doesn't have that 232 contaminant. And in these designs, there's only small amounts of plutonium, and it's really, really poor quality, pretty much impossible to even ever imagine. Denatured cycles, though, and this includes the converter designs, with the pure cycle, it does represent highly enriched uranium. And those three words together will be a non-starter for a lot of people, and it'll be hard to even get them to look at things. But if we run them denatured, there's pros and cons to that, but that makes any uranium completely useless for weapons. It does mean we're going to have a bit more plutonium, and again, it's surprising that there's not a big difference in how much plutonium will be in the salt, but plutonium is a lot harder to remove from the salts than uranium, and it's really poor quality plutonium. It's debatable whether light water reactor plutonium in the waste could ever be really used to make a weapon. In the Th-MSR approach, it's much poorer. It's about triple the spontaneous fission rate that makes things go prematurely, and a lot more heat production. The Th-MSR approach has been singled out in in some studies as probably being one of the highest proliferation resistance of any possible reactor. Rapid deployment capability is basically how much fissile we need to start it. There's also the technological issues. These are any type design is a lot easier to build than light water reactors, but one of the differentiators is how much fissile to start and what type. We don't really have any U-233 in the world. There's a little bit here that we're trying to save in the United States. Spent fuel plutonium, everyone talks about that, but it's quite expensive to get at, and it's also somewhat limited. Fast spectrum, single fluid, or 1.5 fluid designs, they need a lot more fissile material to start, up to about 8 tons per gigawatt electrical. It's still a little less than the fast breeder guys, but it's still a lot. It would impede development. 2 fluid breeders, or any denatured design, we can start those with low enriched uranium. That's another advantage of the 2 fluid design. And then another thing, can we make these small to start? And there's differences there. The 2 fluid designs with what I call a full blanket around them, we can make them pretty much as small as we want. Please don't start thinking we're going to have them in your basements or your car. That's ridiculous, but we can make them quite small power. Single fluid graphite converters, the sort of the neutron budget gets worse as you get smaller, but you're not trying to break even, so yes, we can make those pretty small. The conventional design, the single fluid graphite breeder, and to break even, that is actually very hard to make them very small, of course, 100 megawatt size. And the single fluid fast breeder, the French have the most sort of well-known design, that's very hard as well. Technological uncertainty, that I think is the biggest differentiator in these designs. R&D in nuclear power is expensive, so if we can minimize this, at least for the first generation of designs, we should do that. Fission product removal, it does need a lot of R&D. Even the 2 fluid design, it's a lot simpler in that design, but there's still a lot of work that needs to be done there before you'd have a commercial design. And only single fluid graphite designs don't really need a material that has to be verified as some sort of barrier material that we have to verify in a strong neutron fluence. And going beyond 700 degrees, which the French, their design is pretty much forced to go in that direction, and then you're getting into areas that we don't know the material science that well, a lot to prove there. If graphite is used, some of us, there's different designs that will or will not. We either have large cores where we don't have to ever change the graphite, or we have to prove these replacement technologies. In summary then, all molten salt reactor designs excel in safety, cost, resource usage, long-lived waste. I think the tube and tube, what I've been promoting, two-fluid design, may offer the best overall capital cost and rapid deployment. And then the simpler design, the Th-MSR design, offers the very lowest in technological uncertainty and really, really high proliferation resistance. They all are high. I think this is the absolute highest, though. The inherent features, the physics of them itself, they favor the overall safe waste reduction, cost, and deployment. But they also have a lot of flexibility. We can attain the very highest levels of proliferation resistance. We can run on minute amounts of thorium or modest amounts of uranium with thorium for the utmost in simplicity. There's a lot of things going around in the back rooms that many are not aware of. It's exciting times, but sorry, not quite ready for public disclosure. So. But that's all I have to say for now.
Hey.